So welcome back, everybody, and to a new session. I just wanted quickly to give you some short messages before we move on to today's topic. So you know very well now that we have the official website. And one message which I wanted to give you is that the textbook by Rashka et al., you can download that one for free from the university library. And that is, as we mentioned during the lab session, is normally what we might call a handy textbook. It doesn't contain much of the mathematics, but it has a lot of descriptions about practicalities. And this chapter number 4, which I recommended as a kind of reading today, is also very relevant for project number 1. So project number 1 is something you will find this evening, and we are going to discuss parts of it tomorrow during the lab sessions, and the same on Wednesday. So we will then get started with the project work. At the same time, the exercises you are having this week are exercises which align with project number 1. So that means doing the exercises is also something which is very relevant for project number 1. So you can actually reuse everything you do in the exercises in connection with the project. So the textbook by Rashka contains many nice discussions of things like pre-processing of data, scaling of data, why you do that, and other interpretations, which we will always not have the time to go through during the lectures. But we will discuss many of these technicalities in the lab sessions where we do the more hands-on things. So the kind of idea with the lectures is obviously to give you the more general overview and point to reading material, and also the exercises and the projects we are working on. So I'm going to switch a little bit back to the Jupyter notebook for this week, which you obviously find if you go to the general GitHub address of the course. Just a quick reminder, this is probably the last week I'm going to do this. If you go here, you will then find, if you scroll down here, you will find the weekly material for week 36 and the exercises for week 36, as before. Okay, so the aim today, whoops, there's a typo here. I didn't see that one, regression. And it is an E which has interchanged the placer. I didn't see that before now. Anyway, so we are going to discuss a little bit in the notebook, about a little bit about technicalities about scaling. But what we will start with first is linear regression and ordinary least squares, ridge, which we discussed last week, and also this lasso regression, which we mentioned. And we are going to talk a little bit about their mathematical, how to say, meaning, what actually we end up doing. And then we are going, and this is inevitable, because in every textbook on machine learning, you will see a strong link with a statistical analysis. So we will have to bring in some basic elements from statistics. And we're actually going to derive the same equations we did for ordinary least squares using a probability distribution for the output which we have, the Y data. And then in the exercises session, we're actually going to repeat some of these elements, and we are going to work on lasso, ridge, and ordinary least squares, as these will be basic elements in project number 1. So in a certain sense, we are doing what you might call low-level machine learning, but this is actually part of a standard machine learning tools. Okay, so what I will do now is, before we look into these technicalities, so I'm not going to take that first, but I wanted to remind you a little bit about what we did last week and look at some interpretations which are very relevant for understanding the results which we get. So let's switch to the whiteboard. Oops. So what we did last week was to introduce something which we call ridge regression, where we are optimizing a different problem. And this was originally introduced in a very ad hoc way, where one simply wanted to avoid a possible divergence or the impossibility of inverting the matrix, the design matrix. And you could then add, and this is a trick which you will see in many, many numerical applications, you can just add a non-zero number to the diagonals, and then you can typically invert a matrix. And in a way, this is cheating because you're actually inverting a different matrix. But let's see how we can look at this problem from a totally different point of view. And this leads to a much more elegant type of approach. And it has many, many fundamental, important fundamental consequences for our understanding of the fitting of a model. Okay, so the first thing, or one of the things which we did last week was to perform, so this is a quick reminder, we did an SVD, a singular value decomposition of the matrix X, the design matrix. So this is X, which was then split. So this is just a quick repetition from what we did last week. And we assume that X, or design matrix, has dimensionality n times P, where P is the number of features or properties or predictors, as you may find in other textbooks. And these matrices, U and V, are orthogonal matrices. So they have the property that U times U of T is equal to the identity matrix. And these are matrices. So this is identity matrix, has a dimension n times n. So U is a matrix of dimension n times n. And same with V. This is also an orthogonal matrix. And what we have then is that U, the matrix U, can be written out in terms of orthogonal column vectors. So these are now vectors, even if they have a subscript, U1 up to U of n minus 1. This identity matrix has dimension P times P. And the matrix V can also be written out in terms of the column vectors of n P minus 1. And we have the property that Ui of Uj transposed is equal delta Ij, and V of I transposed times Vj is equal to delta Ij. So these are just a quick reminder of the so-called singular value decomposition we could perform on a matrix. And then we use that to make interpretations. And this is the kind of interpretation which we are going to bring up again in order to get an understanding of what this ridge regression is doing for us. And then we are going to look at some simple examples which we can use to build our intuition about these additional methods. So these were the matrices which we discussed, and then we have this matrix which contains the singular values. No, sorry, not that one. So this matrix contains diagonal elements up to its so-called rank, P, and then the rest are zeros. And these sigma zeros are normally organized either as an ascending or as a descending series. And then we have sigma P minus 1, which is larger than 0. And all the other ones are equal to 0. And this matrix has a dimensionality of n times P, the way we put it up. Now, one of the things we found last week is that we can view the ordinary least square results. So this is the optimal model which we have, ordinary least squares, y tilde. This is a projection in terms of the orthogonal vectors which we have on the output data which we want to reproduce. And this is given as a sum, not over all components, but only over the components where the singular values are different from 0. And this contains now these vectors. So this is a matrix, and this matrix acts as a projection matrix on the original data Y. So that was one of the equations which we derived last week. Another equation which is going to pop up again and again is the derivative of the matrix X transpose. So we have an X transpose times X multiplied, not the derivative, but the V of I is equal to a sigma I squared of V of I. So the eigen values and the eigenvectors of this design matrix we want to invert is actually given in terms of the singular values multiplied with a given vector V of I. So this is very important because one of the properties which we have here is that the sigma i's are larger than 0 by definition. And this means, so we didn't show the full proof, but this means that the standard mean square optimization problem leads to a convex function where all the second derivatives are actually positive. And a small aside here, which we will bring up again. So the second derivative of the cost function for mean squared error, delta beta, and you find that in one of the exercises, is given by 2 over n of X transpose times X. This was one of the exercises last week. And since all the eigenvalues are larger than 0, this translates into this optimization problem being a convex optimization problem with a global minimum. So we haven't fulfilled the proof, but the fact that the eigenvalues are larger than 0 leads us to conclude that this is going to be a convex optimization problem. And that is very useful to know. But there's actually more to the picture than meets the eye here. There's a very interesting property which I'm going to mention, but we will derive it a little bit later. So there is a very important property in statistics, which is called the covariance and the covariance matrix. So how many of you have heard of the covariance in the statistics? Okay, some of you have. So in statistics here, actually, if we now want to use this specific matrix, so this is something which is called the covariance matrix. And you can show that this is proportional to X transposed times X. This is independent of method. So the covariance measures correlations between features. So for instance, if you're looking at housing prices and you have one feature like the number of rooms, another feature which is the number of square meters of the house, another feature could be the number of restrooms, just to give you an example. And it's not unlikely that the price is strongly correlated with the size of the house, number of rooms. So we would expect that there would be kind of correlations among that. So this correlation matrix, which we will come back to, measures the degrees of correlations between different features. So this is a very interesting property because this is something you can set up irrespective of model. Now, for the mean squared error, the interesting thing is actually not only that this is the covariance matrix and we know the eigenvalues, they're always positive, but for the mean squared error as an approach, yes? Yeah, that's an uppercase X, yeah. So that's I'm sorry, sometimes if it's not clear enough from the context. So I'm just mentioning this because this is something we will derive in more detail next week, and you will also find that in an exercise. So for beta, and now I'm putting mean squared error, this is actually proportional. So I'm going to put a subscript J, so it's one of the components. This is actually proportional to X transpose times X inverse of JJ, the diagonal element. So that means it's inversely proportional to the eigen, to the singular value. And we are going to study that property in detail when we are analyzing different models. So the results which we get on the parameters beta, and obviously the variance of the parameters beta, gives us a kind of confidence intervals in standard statistical interpretations, which allows us to make predictions about the validity of our model. Now, one of the problems you will often face is that we have few data, then there can be big fluctuations in the values of beta, and they can have a large variance. So a data poor data set can often lead to large variances and large confidence intervals when we fit a model. So we are coming back to that. So just keep that in mind, because this is one of the type of interpretations which become important for us. Now, one of the things which we also ended up with last week is that the ridge result in compared with what we had for ordinary least squares is given by a sum of a j equals 0 of p minus 1. But now we have these singular values divided by j squared plus lambda multiplied with u of j transpose multiplied with y. So this lambda follows from a new parametric optimization problem. So what we are optimizing now is a new cost function, which is given by the standard one we had for mean squared error of ji equals 0 to n minus 1. And then we had y of I minus. And now I'm just writing a general x. So it doesn't need to be a polynomial. So I just write xij multiplied with beta j squared plus something which we in the literature will see being called the penalizing term or the regularization term or other names. But these are the most common ones. So we have a parameter lambda, which then goes from j equals 0 to p minus 1 of beta j squared. So what we are doing then is to optimize a different problem. And this comes with some pros and cons, which we are going to discuss now. But first, we're going to look at the simpler case. So this is a case when we now take the derivative, as you will also practice in the exercises this week. It means that the beta optimal for ridge is going to be given by x transpose of x, so this is a matrix, plus this lambda times this identity matrix, p times p, the inverse, and then this is multiplied with x transpose times y. So this is roughly what we ended up doing last week, and you will practice some of these things in the exercises. Now, this is a case where what you could have done is actually to add a diagonal term to the matrix x transpose times x. That's the cheap way of doing it, but now we are optimizing a different problem. And when you take the derivative of that cost function, this is the value you find. And the only difference from standard ordinary least squares is that we have this term lambda multiplied with I. Lambda is assumed to be larger than 0. And this is going to avoid having a matrix which cannot be inverted. And as I said, the cheap way this was introduced back in the 60s and 70s was simply just to add a small number to the diagonal matrix elements. And then you could invert the matrix. That's a pretty common trick. But here we can justify it from a different point of view. And this is going to have important consequences for the way we analyze data. And it gives us flexibility because we have a parameter lambda now. So this parameter lambda is normally taken to be larger than 0 or equal 0. If it's 0, then we have ordinary least squares. And if it's larger than 0, this allows us to tune our results so that we can actually get rid of some specific degrees of freedom. And as you will see, if you look at the equation which we have here, this one, if lambda is large and the singular value is small, that means that we are going to suppress degrees of freedom. So it's seen as an efficient way, especially when you have little data, where you can often have fluctuations in the parameters beta, because every singular value here, which you have here, in ordinary least squares is proportional to the inverse of the variance of the parameters beta. So if the parameters vary a lot, it means it has a small singular value. Then we can actually reduce the importance of those parameters which vary a lot. And parameters which vary a lot are parameters which can appear to these parameters beta in case we don't have much data to fit. So often when we have plenty of data, this is close to what we might call painless dentistry, whatever that means. There's actually, when I worked in the US, there was a huge poster, painless dentistry. I don't know what that means. I've always had painful experiences when I went to the dentist. Anyway, but this is, when you have lots of data, it's often much easier to fit a specific model, always. And then many of these problems become irrelevant, which we are going to discuss now. Now, so one of the things which we are going to look at now is a simple case. So we are going to assume now that X, the matrix, is just equal to the identity matrix. And we are going to assume that the P is equal to N. So this is an N times N matrix. So that means that when we look at the ordinary least squares, it means now that Y tilde is equal to X times beta, and this is just going to be equal to beta. It means also that when we now want to optimize, if we look at ordinary least squares, since we have put N equal to P, it means that our mean squared error, or the function we want to optimize, is going to be equal 1 over N of I equals 0 up to N minus 1. And then I have Y of I minus, and then since the model is just beta, and the dimension of P is equal to N, this simply has to be equal to beta Y, right? So I'm just making a simple case now because this model here is going to guide the eye in our understanding of what happens when we introduce this additional term in the cost function which we're optimizing. Any questions, guys? Okay, so if we then calculate the derivative, we do as before, of C of D of beta Y, and we want that to be 0, it's pretty straightforward to see that beta of I, the optimal one, is equal to Y of I. And clearly that means, obviously, that this is identical to Y of I, tilde. So we have a perfect model here, okay? Now, let's now look at ridge regression. So ridge regression, in that specific case, what we are going to have with the same approximation. So then we have C ridge is going to be equal 1 over N. And then we are going to have an I 0 up to N minus 1. And we're going to have Y of I minus beta of I squared, same approximation. And then I'm going to have a beta, no, sorry, a lambda. And then there's a sum over I, and this is beta beta I. Let me just rewrite this one because it got a little bit clumsy. Lambda of I equals 0 to n minus 1 of beta I squared. And then when I take the derivative of this quantity with respect to beta of I equal to 0, it's actually pretty straightforward to see then that beta of I for ridge, and they are the same for all the values of I, is simply equal to y of I of 1 plus lambda. So if you take the derivative, it's actually pretty straightforward to see that. So, and this applies for all the values of beta. They are the same. So if we have 10 values, they will all take the same expression. But they are given by the points y of I. Same expression, but obviously y of I changes because we have different values for y of I. Okay? So now we're going to introduce the next method, which is called Lasso. So what you will see in the literature, there are many ways to optimize a function. Two of the most common ones are ridge and Lasso regression. So what we have then with Lasso, so Lasso stands for the following. So it means least absolute. I always have to write this down because I never remember it. Shrinkage. And we will come back to why we call this for shrinkage. So this is an H, shrinkage. And selection operator. Sorry. So in that particular case, we are optimizing the function. So we call this an L here, just for Lasso. And this is, again, the mean squared error of y0 up to n minus 1. And now I'm just writing this in the general way. So I have j p minus 1 of xij of beta j squared. And then I have plus lambda of a sum over j equals 0 up to p minus 1 of the absolute value of beta j. So this is just a different way of introducing this regularization or penalization term. You will see this written in a more compact way, this term here, as the norm 1. So this function, which you see here, is actually the norm 1 of a vector, where just a sum over the absolute values. Now, the problem here is that when you take the derivatives, you have the derivative of an absolute value. And that's going to give you a discontinuity for values of beta larger or less than 0. Now, if we now look at the simple model, where this X, matrix X, is just equal to the identity matrix, let's just do that and plug that in. So in that specific case, what we end up with is to take the derivative with respect to beta I, which is minus 2 divided by n of y of I minus beta of I. And then I have plus, and now I'm taking the derivative of an absolute value. So that means that I need to have in the denominator of beta of I here, like that. And this is the quantity which we have to put equal to 0. And just keep in mind that when you take the derivative of an absolute value, you have to be careful with the where it changes sign. So many people just put that value to 0 in order to calculate. But this also means, except for this simple case you see here, that in general, you cannot find a nice analytical expression like we have for ridge and ordinary least squares. So this has to be solved numerically. And there is software for that. So in Python, there is a library which is called convex optimization. So CV-opt, I think that's the name of it, where you will simply just set up the matrices and the vectors included in the problem. We are coming back to that a little bit later. But in all practical applications of Lasso, in order to save you time, we are going to use scikit-learn as a library. So you don't need to write your own code for that, because that will take a little bit more time, because you need to implement the derivatives of an absolute value. Whereas when you look at ridge and ordinary least squares, then for ridge regression, you have a nice simple expression for the parameters, the parameter beta, like this one. And for ordinary least squares, you simply have lambda equal to 0. So these are things which we can easily set up and calculate ourselves. So if you look at this simple model, I'm just going to set up the answer here for this Lasso. So let's just do that. This is going to be equal to y minus lambda half. So the factor of a half comes simply from the fact that we multiply away this one. And this is equal to that one if y of I is larger than lambda half. And then I have y of I plus lambda half if y of I is less than minus lambda half. So this should be a lambda here. And 0 if this y of I, the absolute value, is smaller or equal to this lambda divided by 2. So this is just you going through the equations and finding the zeros. It's not so difficult to see that. So I'm just setting it up. The thing which is interesting for us is to plot these results, because that gives us immediately a kind of intuition of what is happening. Okay, should I move on? Is that okay? So if we plot these results, we can now pick any of these beta i's. So we would have a plot of the beta I optimal, and as a function of y of I. So I'm going to put 1 here, minus 1, minus 1, 1, and 1. So if I take ordinary least squares, that is just going to be a straight line. But just imagine that is a straight line. So my handwriting kind of drawing capabilities are pretty limited, as you can see, but just imagine it's a straight line. And this would be ordinary least squares, right? Then if I take Lasso, I would get something which goes like this. So this now ridge, sorry. So what ridge is doing now, if you go back to the expression which we had for this simpler case, you see now that ridge has a quenching of the value of beta depending on lambda. So you pick one value of y of I, and these values of y of I can take any values from minus infinity to plus infinity. These are just our output data. And then you can now make a parameter where you're actually decreasing the value of beta depending on lambda. So this is why this is often called a shrinkage method, because we can reduce the importance of some parameters. If you look at the Lasso, then what happens in that specific case is that we could start something like this, and we go up to minus lambda half, and then it stays around 0, and then it goes up again. So this would be Lasso. So what Lasso is doing is that it is effectively driving some of the parameters to 0. So if you have suppose now you have a y of I, which is larger than 1, then the influence will be smaller than on parameters which lie below 1. then you can actually see a clear reduction of the parameter beta. So this is why this is called a shrinkage parameter. So let's take a look at another way, because this was a very simple model. So let's now assume that we are making a fit with a second order polynomial, but we take out the intercept, and you will see why the intercept is normally taken out a little bit later. So let's look at a case in order to gain some more intuition about what is happening here. So let's now assume that we have two parameters. So we leave out the intercept. And we have only beta 1 and beta 2. So if we now look at ordinary least squares, suppose now that the function we are fitting, so this is a function of beta 1, this is a surface we want to optimize, or the function we want to optimize, which is our mean squared error. So this would now be over 1 divided by n, and then I have I equals 0, n minus 1, and then I have my y of I minus my y of I tilde squared. And in our specific case, this one is just minus xi1 beta 1 minus xi2 of beta 2. So we have two columns in the design matrix. So we're just having two parameters. So you could just think of you fitting a second order polynomial, but you take out the intercept. And as you will see after the break, the intercept is something we can calculate in linear regression with a polynomial fit, which we can calculate from the other quantities. And it's normally taken out in the fitting. So the surface we are trying to optimize is something like this. And inside here, you have the holy grail. So this will be the mean squared error. It doesn't mean that that is the best solution. Okay? So the mean squared error is a kind of measure. It may not mean that that's the best way to describe or optimize the data and find the best parameters. So this is something we have to play around with. Then, if you look at the penalizer, we would have a function here, and that means that that one is going to look something like this. So when we look at this penalty, so when we minimize this shrinkage term, or penalty, or regularizer of j equals 0 to p minus 1 of beta j squared, this has to be just a nice circle, and this will be the point where it has its optimal value, obviously. That's where it has the smallest value. This is a minimization problem. And then what will happen then is that when we are minimizing the whole problem, it could be that this is the case when we minimize min of mean squared error, which is this term you see here, plus lambda of j equals 0, p minus 1 of beta j squared. So that could be the term which gives the minimum for these two terms combined. And for some applications, this may actually be a better minimum than the one which you calculated with, let's say, just ordinary least squares. You don't know that before you've tried it. What you will often see from experience is that if you have something which is well fit by a polynomial, and you will see that in project 1, then ordinary least squares does a pretty good job. So the way to interpret what you're doing now is that you have these two minimization problems by themselves, and each of them have a global minimum. And then when you combine them, this global minimum shifts to another place. So what that means is something which remains to be seen. But this is just to give you a kind of feeling of what is happening. So if you want to if you increase this value lambda, then that parameter lambda will become effectively smaller. If you increase lambda, then the parameters beta 1 and beta 2, if you go back to the expressions which we had here, if you increase lambda, then this parameters beta will become smaller and smaller and closer to 0. And we say that the regularization term is dominating. So if you look back at the equations we had here, like the one for ridge, if you increase lambda, then obviously that decreases beta. And what happens then in your optimization problem is that your optimization problem is then dominated by this term here only. So it's you trying to strike a balance between the two terms in the minimization problem. So large lambda means clearly that the term, which we call the penalization term, dominates, and it drives all the parameters to 0. And you will see that in the examples which we're going to look at pretty soon, that if you now increase lambda, at a certain point, you just get a model which gives you a mean squared error, which is the sum of your output variables, because the model has been driven to 0. And that is obviously a pretty crappy result. Now, if you then go to this ridge, Lasso regression, there is a slightly different way of understanding it. So if we look at Lasso, by the way, this material here, if you go to the textbook of Rashka et al., this is covered in the pages 122 to 125. So it can be useful to look that up because there are nice discussions about these different ways of optimizing the problem. So if we look at Lasso regression, the picture is going to look much the same for the mean squared error. So I'm just going to put the mean squared error here as before. So I have a beta 1 and a beta 2 here. And this is the minimum of the mean squared error. That's the one if we reach, if we do just ordinary least squares. And then if we now look at this new penalizing function, that is actually now given by the norm 1 of the vector. And in terms of these two functions, it looks like this. So it obviously has a minimum. So that is the minimum of this function. This is the min of the mean squared error. Now, the point you see here, that could be min of MSE plus this lambda of beta of 1. Now, the reason why you get this diamond shape is simply due to the fact that you have the absolute values. And that means that if you look at what happens now, in this specific case, which I put up here, beta 2 is equal to 0. So with the Lasso, with one of the parameters, we have actually driven one of the parameters to 0. So in this specific case, where these curves intersect, then beta 2 is equal to 0. So since the contours of this norm 1 function are actually sharp functions, it means that it is more likely that actually the optimal value is located in the intersection between the ellipses and the axis. So I'm doing this in 2 dimensions with 2 variables. It obviously gets much more complicated to visualize this if you go to many dimensions. But this is the basic message. So Lasso is a shrinkage method which actually drives some of the parameters to 0. Ridge, on the other hand, drives them to 0 only if you take a value of lambda going to infinity. But if you have a finite value of lambda, it's going to shrink those parameters which have a small singular value, more than those which have a large singular value, which translates into parameters with a small variance or large variance. So this was a little bit a kind of try to give you a feeling of what these methods are doing. And in practice, what you end up is to set up different functions to optimize, where you then have a free parameter you can tune. And what many people actually do then is, because at the end, when you have optimized a problem, you go back and you calculate the mean squared error. So the mean squared error is a kind of measure. So you optimize it, but with a different function than just the mean squared error. And then when you've done all the optimization, you're happy, then you go back and you calculate the mean squared error, because that tells you how good your model is. And in some cases, these methods give you often a better mean squared error than standard ordinary least squares. But this is something which remains to be seen from calculations. So in project one, you're going to play around with different values of lambda, and we call these regularization or shrinkage parameters. And these give us additional freedom, degrees of freedom in the optimization. So as I said last week, many people get a little bit disappointed when they see all the parameters you include in optimization. Yeah, you have a question? Yes. So no, it's been called L form because it goes back to the norm. So you will see this being called the L form parameters or beta 2, no, norm 2, norm 1. You can actually have different types of norms. But these are the two most used ones. And ridge is perhaps one of the more popular and simpler to implement because you have analytical expressions. So for ridge regression, you can also derive analytical expressions for statistical expectation values. Whereas with the Lasso regression, we have to solve things numerically. So this is just to increment the bag of tools, and you will add such terms when you do neural networks as well, or any other optimization method, which we're going to deal with. And you can think of this as you having more freedom in tuning and finding the minimum value of a function. So at the end, we end up playing with tons of parameters. And that chapter 4 of the text of Rashka has a discussion about how you can do this in efficient ways. The scikit-learn has a library which is called grid search. So you make a grid of the parameters lambda, and then you try to find the best possible representation. Should we take a small break? Is that okay with everybody? Any questions? Or please come. I mean, you can also ask questions in the break, eh? Okay. So as a small intermezzo now, we are going to look at some of the Jupyter notebooks here, because there are some technicalities which we need to keep in mind. So one thing which you will see if you look at chapter 4 in a textbook by Rashka is about the pre-processing, scaling, or normalizing data, etc., etc. Now, many of the examples which I have given you are examples where we set up a data set between 0 and 1. So you could say that data set has already been scaled because I'm using a uniform distribution for the X values. And often the functions which we have, they vary little. So they could vary from, let's say, -5 to +5, just to give you an example. So that means that in a certain sense, there is no need to scale your data. And also in project 1, when you look at the question, do I need to scale the data? You may say, look, this function here doesn't vary a lot. And if the function varies from 0 to 10, there is often no need to scale the data. But if you have variables which vary from, let's say, minus a million to 10 billions, then you should think of scaling the data. Similarly, if you have variables with many different units, it may be useful to scale the data. One thing, so in this data set, you're going to have the first one on project one. This is going to be a simple function which we will generate. But you can have cases where you actually need to look at the data. So we had a case where a master student spent 2 months to realize that the data were taken at different intervals and tabulated in different units. And we couldn't make head or tail of the data because some of the inputs for the wind velocities were in kilometer per hour, whereas other ones, which had been taken 10 or 20 years earlier, were in meters per second. So unless you look carefully at the data, so actually it's one thing which we always recommend when you have a data file somebody gives you, take a look at the data file. They can often be pretty messy. And there will often be things like data which is not there. So you will see sometimes not a number, none, in columns. And then there are ways to replace not a number. So what many people do is that they replace that with the mean value of all the features in that specific column, if you're missing data points. So take a look at that chapter 4, because it has many hints and tips about scaling the data. Now, the thing I wanted to say a little bit about now is something which always leads to some confusion. And this is in particular relevant when you're dealing with linear regression and you're fitting, for instance, a polynomial. So you've probably seen that the intercept just gives you ones. So it's pretty common in the fit to take out the intercept and then recover the intercept from the other parameters you calculated. So if you look at the slides here, these are things which I'd like you to look at. We will discuss these at the lab as well, but there's a lot of these kind of small tricks and ways of pre-processing data which are important to look at. And if you have large variations between features, it can be convenient to actually scale them. And one of the things which many people do is actually to subtract the mean value for each column and then fit the data, because subtracting the mean value from all the elements in the column can often help in terms of outliers. So if you have big variations, subtracting the mean value hopefully gives you something which has less variation. So there are many such small tricks and or pre-processing of data. So you will see things like the standard scalar, which is a function which actually, it's a little bit, how to say, misguiding the name, because what it does, it subtracts the mean value for each column and then divides also by the variance. But normally you don't have the variance, and if you have don't have the variance, you set the value to 1. So in some cases, you may have experimental data where you also have a prediction of the standard deviation and the variance. And then you would typically scale that by subtracting the mean value of a given column, given feature, and divide by the variance. So some of these functions do this automatically, and there's something which is called the standard scalar in scikit-learn. So if you need to scale the data, not doing so will give often an unfair penalization of the parameters, since their magnitude depends on the scale. So the predictor is also something you will see as a name for the feature or the properties. So depending on which text you're looking, some people call it the predictor, some people call it the feature, etc. So predictor is just another synonym of features. So what you will then see is that the specific feature can actually depend or give an unfair penalization here. So when you transform your data and before training a model, the same transformation needs to be done on your eventual new data set before making a prediction. So that means that what you would typically do then is you have a train mean, where you then simply calculate the mean for the y values, and you do the same for your feature matrix. And then you can subtract that one from the training and from the mean. And then you have some train model where you just now train with this kind of data where you have subtracted the mean value. And then when you look at the test model you have x test minus x train mean here. So that means that you use the mean from training data. And this is how you would make the prediction. So there's a way to see this. So the math here, I just wanted to go through this via slides, but I invite you to take a look at it in connection with project one. Because when you're comparing with scikit-learn, scikit-learn does something by default. And if you include the intercept, you may not get exactly the same things as scikit-learn prints out for you. You get the same coefficients, but you have to be careful in interpreting the data. So if you now look at what we are doing in the optimization, so this is just a mean squared error. So what you have then is a derivative of respect to beta j, which you want to drive to 0. And this is what this actually looks like, okay? So I anticipated that you can actually pre-calculate or calculate the intercept by using the other values. And I will show you how you can do that. So in taking the derivative of the intercept, you have this equation here. So this is you simply going back to the mean squared error, where I have singled out the intercept, because that doesn't multiply with any of the x's. And then what you have is this equation here. And then you can separate it. I multiply away this parameters 2 over n. And then you have simply beta 0, the sums. This is just a constant. So that means that this becomes n times beta 0. And then you have these terms. And then you have these terms as well, where beta 0 is not included. So that means that you can define beta 0 in terms of the mean value of the output minus the parameters here. And if you now only have beta 1, only 2 parameters, you're fitting a straight line just to make life simpler. But in principle, you should have all the other beta values. Then you can, when you have calculated beta 1, these are known quantities. And actually, this is just the mean value of a given column. So that means that what you would have then would simply be you subtracting the mean value of the output, and then the mean values of the given columns of your feature matrix, except the intercept guy. So that means that you end up with this expression, and the more general one would actually be that one. So when you fit without the intercept, you can always recover the intercept from that expression. Okay, in linear regression. So this is something which applies to linear regression. And it's a special case with you fitting a polynomial, because then the matrix with the intercept has just ones. So that means that if you calculate the mean value of that, you would have, and subtract it, you would have zeros in that column. Because if you have just ones and divide by the number of particles, no, the number of observations, that gives you simply n times n, which is 1. So if you subtract that, if you subtract this mean value, which is pretty common when you're scaling your data, then the intercept column would just have zeros. And that would lead to problems in your matrix inversion. So just think of that. You can keep running the calculation when you don't scale the data or subtract this mean value. So try it out in both the exercises and the project. The benefit of doing that is hopefully that you put less emphasis on outliers in the optimization. And also you can recover, in linear regression, you can recover the intercept immediately by that formula which you see there. Okay? So just be a little bit careful with how you do the optimization. And especially when we come to lasso and ridge regression, if you use libraries like scikit-learn, the intercept is not included because the intercept can be large and that can penalize your mean squared error. Okay? And you will see some examples here as well. So I'm just going to go down here a little bit because you can see there's an example here where we now fit a function. We set up the design matrix. These are the true values of beta. So I'm just setting up a polynomial here. And this polynomial is now x to the power of p times b. And then with these are parameters which I have. I do a polynomial of degree 3. And I can include the intercept in this formula here. And then I fit, and then I do my linear regression. I print the true values for beta. And I can also do the same thing with the scikit-learn. So SKL, here's my scikit-learn prediction. So if I do that, and you will see now that in this specific case here, when I do the fitting, the data, so in the scikit-learn, I've used an option where I put fit intercept false. So that means it includes the intercept here. So the intercept is the value of output target variable when all our features are 0 and our function crosses the y-axis. So you can, if you also look at the other case which we have, you can also not include the intercept in the design matrix. And now we're setting up a polynomial which excludes the intercept. And in that specific case, I do fit intercept with the scikit-learn where I have intercept equal to true. And then I should get the same results. And as you can see here, I have the fitted beta, the scikit-learn fitted beta. And then I do the fit without the intercept. And now you see that I get the beta 1 and the beta 2 variables, which are the same here. And I can then recalculate the intercept from that formula. So you can fit with the intercept or without. So the thing is that what you have to pay attention to is when you do this standard scalar, because then a library like scikit-learn takes automatically out the intercept column. And if you include that one in your calculations, you will not get exactly the same as scikit-learn. So these are some kind of technicalities which sometimes takes a little bit of time just to get used to. But the kind of default which many people do is to take the data and subtract the mean value for each column in the feature matrix. And then you can also scale the data in the sense that if your data span from, let's say, minus 100,000 to 10 billions, you could scale your data down to a smaller domain. Because you can also risk when you have large spans in your values, when you're inverting matrices, there is always the risk of what we call losing numerical accuracy when you have a large range in the values. So one thing is to take out the mean value, which comes with the standard scalar. The other one is actually to normalize your data to a smaller interval. And scikit-learn has this functionality. So there is a normalizer, there is a standard scalar, and so on. So take a look at these functionalities here. So this is just a kind of warning, or not warning, but you having to think about how you look at your data. So for the first part of project 1, you don't need almost to think about these things because you're going to produce numbers between 0 and 1 or a very small domain. So the data already normalized to a small domain. And there is no big variation in function values. But then at the end of the project, there are data from topographic data about landscapes. And there the data can vary a lot. And then it's convenient to actually normalize your X and Y values. So you're going to get the X and Y values of a landscape and the height of mountains or whatever. So obviously, if you get a landscape data from the Midwest, it's actually dead flat. So That's pretty easy. That you can almost fit with a straight line. But if you take a fjord in Norway, it's going to be pretty up and down, and it's going to be difficult to fit. Okay, so this was a little bit about the scaling. And then there is another example when you now use scikit-learn and Lasso regression. And in this case in particular, when you optimize the problem, the intercept is always taken out. So if you write a Lasso code or your own ridge regression, and you include the intercept and you want to compare with scikit-learn, you may not get exactly the same. So the optimization in that case is actually done on, not on these parameters which you see here, from j equals 0, but actually from j equals 1. And the same is with Lasso regression. And that means that when scaling the design matrix and the output targets, by subtracting the mean values, we have an optimization problem which is not penalized by the intercept, because the intercept can be large. And sometimes you want to leave out large terms. And that means that you can, it's not, you may not always get it, but you can get a mean squared error which is smaller, since it focuses only on the remaining quantities. But if you bring it back, so you can always do that when you write your own code, you can do the fit with the intercept. But beware then that the intercept can be large and it can bias the optimization problem. So the codes which you see here is actually the same kind of vanilla cases which we have been discussing again and again. And in this case, I'm setting up the mean squared error, as you can see. And I have my x values, just a random number between 0 and 1, 100 numbers. And then I have an exponential. And just to make my life much, much easier, I've actually taken away noise so that we will normally get a pretty nice fit. And then I'm making a polynomial of a given degree. So I'm fitting a polynomial up to degree 20 in this case. And you can now see I have a function where I'm setting up the polynomial degree. And here I include the intercept column explicitly, as you can see here. So this function which you see here is something which will also be relevant when you do project 1, except that then we are going to have a two-dimensional function. So you will have to have x and y as well. Now, what I'm doing scikit-learn and also my own code. And in this particular case, I'm doing ridge regression. And I'm setting up my own ridge. And then I have my ridge prediction, which I make with scikit-learn. So that will be this function, which you see here. And then I put the intercept false, as I mentioned. Let me just see, there's a question here. Yeah, that goes up to degree 19. Sorry, when I put 20, it goes to degree 19. Thanks. So my own ridge regression, I have these parameters lambdas. I pick lambda values from 10 to the minus 4 to 10 to the 2. And I want to have 6 values in that region. This is a very brute force way of doing it. Scikit-learn offers you a functionality which is called grid search, and it tries to find the optimal value for lambda within that domain which you've chosen. And this is normally what people end up using. So what I'm going to do is to do it by the eye. You will be surprised by a quantity like the chi-squared. Have you met the chi-squared error? Which is actually the mean squared error. We have something which we call chi by the eye. So many people tune parameters, and then they do it by the eye and they say, hey, this is the optimal parameter. Instead of just optimizing it like we are doing here. So I'm going to do chi by the eye, or mean squared error by the eye. And in this specific case, you see now that I'm training my ridge regression, do it by matrix inversion. I add the parameter lambda here. And then I let scikit-learn do it. And then I have my y tilde own ridge, which is x train times. In this particular case, I have not subtracted anything. No, so this is just the design matrix is just plugged in as it should. So I'm not subtracting the mean values here. And then I'm making the prediction with my own code and ridge, and then I'm making the plot here. And there are two things to watch here. If you look at the plot first, now let's take a look at the plot. And you see that the two agree. So on the x-axis, I have log 10 of lambda. And you see now that for very small values of lambda, what I'm getting is a mean squared error, which is basically 0. Actually, in this case, the mean squared error, which I'm calculating with ordinary least squares, is close to 0 with that polynomial. And you see that here. But then I start increasing lambda. And if you think back to what we discussed before the break, what is happening now when I increase lambda is that I'm driving the parameters beta to become smaller and smaller. So when I drive them to become smaller and smaller, what it means is that this term with y tilde here is going to vanish. And then you will see that the mean squared error increases. And this is what you see here. So after a certain region, this starts increasing. So for the mean squared error, after I've done the fitting of the models, it seems that the standard optimization with ordinary least squares is the one which gives the best result. Now, one thing which is useful to look at, and this is actually to print out the values. So take a look now at the values. So in the beginning, I have a lambda which is close to 10 to the minus 4. And you see now that the beta values, so I have 20 of them. The first one is the intercept. And you see all the other ones are pretty small. So in a sense, when you include the intercept, that is something which can be larger than the other quantities. So you see now that beta 1, beta 2, etc. are pretty small here. So the fit is getting pretty good. And you also see a mean squared error, which is 10 to the minus 7, which is pretty okay with a 19th order polynomial for these exponentials. And you see that the high order parameters, they oscillate a little bit. We are coming back to what that can mean. But then when I am now increasing the value of lambda, if you go down now, you will see that some of the parameters here tend to become smaller and smaller. So what I'm doing now, I'm driving with this parameter lambda, I'm making some of the degrees of freedom less and less important. So if I have a 19th order polynomial, the components from 19th, 18th, 17th order are becoming smaller and smaller. So this is effectively what ridge regression is doing for us. So it's very, how to say, relevant when you have little data, because then you can have some parameters which become large, and then we can try to quench them because they will fluctuate a lot. The reason why they will fluctuate is that when you make a large model for small data, is that you're forcing your model to go through all the data points, and that can lead to large fluctuations from model to model. So, and you can see now when we go to the last value, you see that some of the parameters are really getting 10 to the minus 3 something, and even the intercept is getting smaller. So we are effectively shrinking all the parameters. And when you look at the final mean squared error, it means simply that your model is diminishing in importance. And then the mean squared error blows up. Now, when you're playing around with different types of data and different models, you may actually see that ridge regression can give better results than ordinary least squares. But that will always depend on the amount of data you have and the model complexity. So this is something you would have to play around with for every model complexity and find the optimal mean squared error with ridge regression, ordinary least squares, and lasso regression. And this is essentially what project number 1 is about. Doesn't sound too exciting, does it? Actually, machine learning is tuning these parameters. And if you go back to these large language models, we have trillions of parameters, really. And many of these parameters are parameters you can give a specific meaning to. So often one of the difficult things when you train a machine learning method is to get an intuition from what you have achieved. What gives you the minimum and what are the optimal parameters and what they mean. That is the difficult part. Okay, so let's go down. There's a further example with scikit-learn with Lasso as well. So this example is pretty close to the previous one, but now you can see that I have included down here. Actually I do this only without the intercept, sorry. So in this specific case, I'm performing all these examples where I take away the intercept, and I also scale my data by subtracting the mean value. So I'm repeating the same thing which scikit-learn is doing, but I do this by hand. And this is essentially, but now I'm just fitting this without this quantity and the intercept, and then I can always extract the intercept. And you can see now that to numerical precision, scikit-learn and my code give essentially the same result. And then you can calculate the mean squared error. And one of the things you can see when you compare with the previous case is actually that the mean squared error tends to become smaller because we fit it without the intercept. So this is with scikit-learn and just ridge regression. And if you scroll down a little bit more, so you see again the same kind of trend as we had before. And then you can do the same thing with ridge and lasso. And this function here is essentially the same as before. And we fit this one without the intercept. And here you can make a comparison between ridge and lasso. And what you will see then, which is a little bit more interesting now, is that lasso up to 10 to the to a lambda parameter, which is 10 to the 10. The standard ridge on the test data is basically pretty small. But then you see now that lasso here is blowing up, and that is because lasso drives the parameters beta to 0 immediately. So ridge has a scaling which goes like the singular value squared divided singular value squared plus lambda. So it's only when lambda becomes extremely large that the parameters start vanishing. Whereas lasso puts some of the parameters to 0 after very few values of lambda. And you can see that here, when we now print out the parameters here, you would then see that the first parameters you see here are those from ridge regression. And then the final ones, which you see here, so this is lambda equal 10, you see now that these parameters are driven to 0. And then your error is just blowing up here. So ridge is one way to drive slowly the less important parameters. So you're producing degrees of freedom, which are effective ones gradually, whereas lasso can shrink some of the parameters to 0 immediately. So this is essentially the kind of wisdom I want you guys to extract when you play around with these different methods. Take a look at these codes because they are very relevant for the exercises this week. And I will bring them up again during the exercise sessions. So I'm going to repeat this thing because it takes some time to simply get used to it. Okay? So I wanted to use the last 15 minutes or 30 minutes to introduce the statistical interpretation, because that's something we will deal with next week. Also, when it comes to the connection with what's called the bias variance trade-off and overfitting and underfitting. So how we can extract a measure for these quantities. Because when we are going to make the as you saw in exercise 3 last week, you found an optimal complexity for a function for the test error. And the question is now, can we find one way to understand that at a deeper level? Then we need some statistics, because we are going to rewrite the mean squared error in terms of the variance of the model, and something which we are going to call the bias, which is the difference between the mean value of the model and the test and the output data you have. So let's go back to the whiteboard and take a look at, let me bring that up. So I normally don't like to bring in a new topic towards the end of a lecture, but it's just to get started for what will come next week. And this is actually part of machine learning, which many people may find a little bit difficult, because we have an unfortunate situation that not everybody has taken a course in statistics. So different bachelor programs put less or more emphasis on that. But I hope I can guide you through the essential elements so that you're left with a hopefully a better understanding of what is going on. So let's look at the statistical analysis, because that's something we will discuss next week as well. And there are some quantities which are very important for us. So one is obviously expectation values, like the mean value and other types of expectation values. We have the variance and the standard deviation. We have something which is called the covariance, which we will also discuss next week. And then we have other properties, which we are going to bring in when we need them. And obviously, a very important thing is a probability distribution function, PDF, probability distribution function. And you met things like a Gaussian, right? That's an example of a probability distribution. And the thing is that when you look at machine learning as a field, in many, many cases, we've been very, very, how to say, concerned with fitting the data to a model, like we did now with linear regression. But linear regression, the way we have done the fit, doesn't give us a probability distribution unless we do some more laboring. The nice thing with a probability distribution is that you can estimate the errors of your model. And you can ask the question, what is the probability of B given A? So causation becomes a very important aspect. When we make a prediction like we did till now with ordinary least squares, we can fit the model, and then we can predict new results. And we can also find correlations among the data, which we will discuss next week. But we haven't a probability distribution. So often in science, we are more interested in that. Actually, ChatGPT and all these models, they're called generative models because they produce a probability distribution. So you train on cats, and then you train a probability distribution, and then you tell the probability distribution, make a picture of a cat for me. And in the previous days, when the training was not optimal, you could get cats with 6 legs, things like that. But now they've gotten much, much better. Okay, so there's a basic assumption about the data, which we need to bring back. And this is basic assumption for this type of regression problems. So regression means essentially fitting a continuous function. I should say, in many cases, we don't care whether we have discontinuity. We make a fit anyway, and then we hope that that fit works well in the regions where the function is not discontinuous. So the basic assumption is that y is equal to f of x, and we mentioned that in the very beginning, plus some epsilon. So this is what we call a non-stochastic variable, a non-stochastic function. This is an O. And this should have, just a moment. This is, I should write it correctly, non-stochastic. Whereas this is a normally distributed noise with a zero mean and a variance of sigma squared. So that's a basic assumption about the data. And this is what Gauss actually made when Gauss derived the ordinary least squares equation from a statistical point of view. Have you seen that derivation? It's pretty common in statistics text. But let's try to do that and see, or let's outline it, because we pick it up the rest next week as well. Then we have the important quantities like expectation values. And if we assume that we have a continuous probability distribution, so the expectation value of this variable epsilon, that is the mean value, this quantity here. I will often write the mean value with a subscript referring to the variable. And this is given by an integral, if you have a continuous probability, of x defined in a domain of variables, of d of x. And then I have this epsilon, and epsilon may depend on x or not. So let's just write it like this. And then I have the probability for this specific function. And for the noise, which we have, this is set to 0. We just made an assumption. Then we have another quantity, which is the variance of this quantity epsilon, the noise. And that is given by an integral over x minus epsilon squared. And this has a probability p of epsilon of d of x. And we just define that one as sigma squared. And the probability of this p of x is now given by a standard normal distribution with zero mean value, square root of the exponential of minus x squared divided by 2 sigma squared. So that's a standard normal distribution, which means that we set the mean value to 0. Does that sound familiar? Seen before? Many countries in Europe, there's a kind of, there used to be, and there still is, a kind of idea that grades should be normally distributed. I don't follow that idea. I was normally distributed when I went to high school. I didn't like it because there was only one who should get the top grade. And I was perhaps one of these kind of unruly kids, but I always tended to have everything correct, but I never got the top grade. Because the teacher said, I mean, there's a distribution here and I have to follow that one. That's not very pleasing. Sorry, that was a digression. So what we did next is to assume that this x times beta, this is the model which we made, is an approximation to this function f of x. So that means that y is now being approximated to x times beta plus epsilon. So this quantity is non-stochastic. So that sounds reasonable because think of this matrix X. this matrix X could represent you having made a survey where you have specified all the parameters. So there is nothing stochastic with it. You can make an experiment where you fix the velocities of particles and so on. So everything is something you can fix. You can complicate things, obviously, by saying that X follows a distribution. But now we're going to say that X is a non-stochastic object. And beta, as you've seen, is also given by a deterministic algorithm in terms of defined quantities. So the only stochastic part is actually this epsilon. And this y of I is then, when we write it out now in terms of the model, is given by this sum over j equals 0 to p minus 1 of xij times beta j plus some epsilon of I. So each epsilon of I has the same noise, same function. So if I calculate the value of this quantity, then this is the same as the expectation value of a non-stochastic variable, which is the expectation. So I'm going to rewrite this quantity here. So let me just rewrite it like x of I, and then I put an asterisk to indicate that I'm doing this multiplication. So this quantity here is something I rewrite like that, but just for compactness. So I'm going to calculate the expectation value of this quantity, which is non-stochastic, and that is equal to itself, because we don't have a probability distribution which governs these quantities. So that means that I can take any probability distribution and I will always get the value itself, because it's like a constant. It doesn't depend on a Gaussian, like the Gaussian for the epsilons, etc. So these variables, the probability distribution we have assumed, doesn't govern these quantities. So that means that this expectation value is just equal to this quantity itself plus E of epsilon I, which we put to 0 by definition. So it means that we have a value for the expectation value of y of I. The next thing, and I'm just going to set up the result, and this is where we will begin next week. So we are going to find the variance of y of I, and I'm just going to state the result. So next week, and also the exercises next week. So next Monday, we will actually discuss these quantities. And this means that we can infer that this y, since we now have, so this is the variance of the epsilon, then we can infer that y of I follows a normal distribution, 1 over 2 pi sigma squared, square root, exponential, and then I have minus y minus xi times beta squared divided by 2 sigma squared. So we made the assumption that the x's are non-stochastic variables. X times b is also a non-stochastic variable. And that defines the mean value of y. But then the epsilons are defined to follow a normal distribution. So then we infer from that that y should be given by a normal distribution where it has a specific mean value and a standard deviation. So this is a basic assumption about the output. You can make life more complicated and make an assumption about the input as well. But now we're assuming that the input is non-stochastic. And this is what Gauss assumed back in 1850. And then what Gauss did was to maximize the product of all the probabilities for the individual ones. And then you will get exactly the same equation as ordinary least squares gives you from a standard linear algebra point of view. So next week we will start there, and then we will do more statistics, and we will discuss the bias variance trade-off as well, which is going to be an important element in project number 1. Okay, guys, thanks for your patience. You're too kind. Okay.